So welcome everybody. Thanks for your time again today. This is a webinar as part of the Australasian Coastal Restoration Network that Megan Saunders from CSIRO and myself from James Cook University are facilitating. We're really pleased today to have Professor Neil Saintilan from Macquarie University. I'm really excited about the talk today, Neil, so no pressure. I'm really keen to hear about what you've been working on. I've read your papers.
I'm excited too, Nate.
So really appreciate your time today. I just want to start really off by acknowledging country. And for me in Townsville here at JCU, we're on the Bindal and Woolgooroogabar country, and pay our respects for elders past, present, and those emerging. We work a lot with traditional owners in our lab, in our group, our university across North Queensland and Northern Australia. And everyone on this call, I'm absolutely certain, works a lot with traditional owners, and we do so in a respectful way. And I just want to make sure we acknowledge that as part of this webinar series. So as I mentioned, we're fortunate today to have Neil give us some time to talk about his work on mangrove dieback and restoration and strategies. And from my end, I think we're good to go. Katie, thumbs up. Yep. Okay, I'll open the floor to you, Neil, and thanks again.
Thank you very much, Nathan, and thank you very much for the introduction. And I'm coming at you from Wadamadigal country, the Eora Nation. And, you know, the environments, as you would know, that we're talking about today of tremendous significance to Indigenous people. And something we need to be cognizant of is that our actions often have deleterious effects on these wonderful places. But I'm hoping that it's a more positive kind of talk today. I'm going to be talking about mangrove dieback, but also restoration. I'm going to be talking about the threat of climate change, but I hope not in a nihilistic sense, more practical sense. And a bit of an outline, mangrove dieback example. So I'm going to start with some really practical examples, a bit of a scattergun, I guess. And by the way, my colleague Patrick Dwyer is pulling together like a bit of a fairly extensive database on mangrove dieback and causes around the place, and I guess this will contribute to it. This is more my experience in what is coming up to, I guess, 40 odd years of walking through mangroves. It's me as a younger person on the Hawkesbury, and really a range of causes of mangrove dieback. And so when you see dead mangroves, you know, there can be a lot of different drivers of that. And so I guess this is the first half is my perspective on what might be going on and how you might identify why you've got some mangrove dieback where you are, and their vulnerability to dieback, both climatic, whole range of causes, geomorphic and so forth. The second part is going to be a little bit more theoretical, kind of delving into some recent scientific work on exposure and vulnerability of mangroves to sea level rise, and what we're currently thinking about how what are some of the upper thresholds of sea level rise when mangroves get into trouble, and when are we likely, and under what circumstances are we likely to meet those thresholds? So that's kind of the second part. And then at the end, you know, some really practical considerations about what sort of environments might be suitable for mangrove restoration projects today that are resilient to longer term drivers like climate change. So, you know, in terms of mangrove dieback, I'm just going to go through a few things fairly quickly. I'm starting at Tara Point, and they're not mangrove stumps, they're Casuarina glauca stumps. They're she oak, swamp oak. And these are exposed at a fairly important place in Australian history. This is quite close to Cook's landing site in Kurnell, and it in front of a wetland, a freshwater to brackish wetland that was actually visited by Cook and Banks, the crew of the Endeavour, and was part of their part of them gaining fresh water that they needed for the Endeavour. And just in the last 2 years, the sea's broken through and completely salinized the whole thing. And you can see the dieback of the brackish and freshwater vegetation behind it. The only reason for mentioning that, aside from the historic curiosity, is that this is an example of the way in which lateral kind of erosion, so geomorphic processes, can have a deleterious impact on wetlands, even wetlands that have been there for millennia. And this is probably, I'm not an expert on the hydrodynamics of Botany Bay. This is probably a sort of a delayed effect of the third runway in Sydney Harbour, changing the wave climate, exacerbating erosion at Tara Point, and there we have the breakthrough into sort of an historic significant wetland. So are mangroves vulnerable? And thinking in the context of mangrove restoration, we need to be thinking a little bit about lateral patterns of erosion and accretion. And we've got historic time series. Google Earth gives a bit of a sense of patterns in changing shorelines, also DEA coastlines from Geosciences Australia. Excellent resource that gives us long-term data on how shorelines are changing. And that can give you that context for understanding whether your site is subject to lateral erosion. Because you don't want to be planning, wetlands, restoring wetlands that are just in the path of these kind of processes. There's no stopping them, really. There's the casuarina forest dieback into this sort of historic little wetland on Tara Point. Second example, hail damage. Who'd have thought? This was an intense hailstorm that hit the Hawkesbury River in 2003 and absolutely shredded this Sardinia forest. And I walked through it. Council wanted to know what was going on. I walked through it. I noticed that the skyward side, the upper side of the branches were really, really heavily damaged. Underneath, perfectly pristine. And in fact, seedlings entirely untouched that were protected by horizontal branches. And you could see the hail marks on branches and leaves. So intense that entire forests were completely denuded of leaves. Very rare event, but I checked the radar and it's the only time I've seen the radar actually black going over the Hawkesbury River. So that was a pretty good indication as well. That was actually hail shredding. The good news from that is that the canopy was completely restored even within a few months. It was up at around 60% restored to what it was previously, and pushing up toward 80% within a few years. Third example, again from the Hawkesbury River. And this is associated with an East Coast low in 2021. And I'm going to come back to that East Coast low a few times because it keeps cropping up. When people talk about mangrove dieback events in New South Wales, that one East Coast low pressure system is often involved. And that's true of some dieback in the Port Hacking estuary. It's true of dieback in the Hawkesbury River estuary. The next example I'm going to go on to, the Mile River mangrove dieback, same event. So it's pretty significant, but differently manifests in each of these different estuaries. And here on the Hawkesbury, we noticed mangrove canopy dieback. It's hard to see in this photo, but you're comparing the left-hand and the right-hand image before and after. And here you can see the 2020 image, beautiful, healthy mangroves. 2023, you can see that grey band in the frontal mangrove strip where the canopy has died, the Abyssinia marina canopy has died back. And a ground level photo, more obvious here. I'm on the right hand side, I'm in the mangrove and you can see the bare canopy. On the left-hand side, a ground view of the canopy is very obvious there that you've got the Avicennia has died back. And I use the term dieback advisedly. We're not here assuming mortality. And one thing that you've got to keep in mind about Avicennia, if it's stressed, it does tend to drop its leaves. And that's partly a survival response because it doesn't want to be losing water unnecessarily. If it's struggling to respire, it will lose leaf. If the water's getting too saline, it will lose its leaves. It's in a sense nervous about having a huge leaf area, huge exposure to water loss under adverse circumstances. So it's a natural response for Avicennia to drop leaves. It looks dramatic, doesn't always mean mortality. What we found on the Hawkesbury was that wherever the mangroves had more than 8 centimetres of fresh sediment deposited over the pneumatophores, they lost all their leaves. If it was between 4 and 8 centimetres of fresh sediment, there was partial defoliation. Where we didn't find fresh sediment, we tended to find the canopy intact. So there seemed to be a threshold response here that the flood of 2021, and there was a follow-up flood the following year, brought enormous amounts of sediment through the Hawkesbury system. And the pattern of sedimentation wasn't universal, it wasn't ubiquitous. There were some point bars that had heavy sedimentation, others less so. And the gradient of canopy dieback followed the gradient of sedimentation. There was a threshold effect, 8 centimetres, almost complete canopy loss, right? Because they couldn't breathe. The pneumatophores, the breathing tubes of the Avicennia, were covered. They were suffocating, lost their leaves. Now, what you might find, and we've seen this before, I'm thinking of an example from Homebush Bay, was that eventually the pneumatophores will grow above that fresh sediment. They'll start to breathe again and the canopy will eventually be restored. Now, there may have been some mortality, but I think we've still probably got to wait a few years to see whether these trees are actually dead. They can go for a few years without having any leaves on their canopy, then grow back. This is something we've got to be a bit careful. Dieback, yes. Mortality, maybe have to wait and see. The other interesting observation here was that the other species in Sydney, we only got 2 species of mangrove in Sydney, Avicennia marina, the grey mangrove, and Ageceras corniculatum, the river mangrove. Ageceras was completely untouched by the sedimentation events, had no deleterious effect on Ageceras whatsoever. And that's dramatically illustrated in this photo. The understory here, beneath the dead Avicennia canopy, is the river mangrove, Ageceras. It doesn't have pneumatophores. So in that sense, there were no pneumatophores to suffocate. It breathes through lenticels on the lower stem. And so it's less exposed to that sedimentation issue compared to Avicennia. And there you can see strong regrowth. Mostly, this is a few years later. I think this photo was taken in 2024. Very strong regrowth, fresh sediment, laden with nutrients, mangroves re-establishing very, very strongly, mostly the river mangrove, not Avicennia marina. And so it'll be interesting to see how this plays out. Maybe over time we're seeing, as we get hydrological changes in the Hawkesbury River, with these short, sharp flooding events perhaps becoming more frequent under climate change, we'll see a shift from the grey mangrove to the river mangrove. Something we're already seeing, I think, in the Hawkesbury over the past few decades. Very, very strong, almost dominance of the river mangrove over Abyssinia. That seems to be continuing. My final, I think, example is the Mile River. The Mile River is to the north of Sydney and Newcastle. It drains the Mile Lakes, Ramsar listed Mile Lakes, into into Port Stephens, and it's so Mile Lake's freshwater system, and the Mile River is tidal at Tea Gardens, and where it's tidal, we have mangroves. And here is a before and after photo. 2020, this is part of what I could show you as a much broader area on the Mile River. And you can see the fringing mangrove vegetation. If you compare those two images, left and right, you can see the grey dieback of mangroves and the fringing mangroves. To put some scale on it, we're talking between 50 and 100 metre wide dieback zone. And it's very strongly controlled by elevation. And there's a clue. It's a different pattern of dieback. Even though it's the same East Coast Low event, it's a different pattern to dieback on the Hawkesbury is really patchy and sort of like point bar dominated. Here it's much more widespread, but at a specific elevation. Essentially, we now know anything below 0 meters AHD died in this event. And here is a photo from just a few weeks ago. So we're now in this photo 5 years on, and you can see we are talking dead mangroves here. They have ceased to be. They are not coming back. There's zero recruitment, nothing, no mangroves. You'd be thousands of propagules coming into this site every year. None of them are surviving. So we are no longer looking at a habitat suitable for mangroves. So that's interesting. What's going on in this case? And I think now this looks like one graph superimposed on the other. It's not. The graph above is daily rainfall, starting at 0. And you can see the East Coast low pressure event in, I think it was the end of March 2021. So you had daily rainfalls up around or higher than 50 millimetres for several days, total rainfall well over 200 millimetres, right over the Mile Lakes. So, up where between a sort of, I guess, the 50-year rainfall event, possibly higher, big rainfall event. Now, the graph below is water level, and you can see what's happening to the evacuation of the tide, the effect that base flow coming from the Mile Lakes through the Mile River, the effect that base flow is having on water level at low tide, and it's elevating that water level by about 1/3 of a metre. So instead of March, where you're getting down to 0.5 metres AHD, during April, right through the end of March, right through April, it's never getting lower than about minus 0.2 metres AHD. And it's not until we get into right at the end of April that you're starting to get the low tide actually draining out completely. So my hypothesis here is that the continued high base flow of the Mile River after that East Coast low pressure event draining the Mile Lakes elevated the low tide above the pneumatophores of that frontal strip of mangroves, killing them. And what's happened then? Okay, why is there no dieback? And I'd offer you two reasons. One, when mangroves die, their root system collapses. And I guess that's a difference between mortality and dieback. Dieback, the mangrove root system's still alive. Mortality, the root system dies. And if you've ever seen mangrove roots, they're mostly airspace. So if the mangrove root system dies, it's like letting the air out of a tire. The whole thing just subsides. And it'll subside up to 10 centimetres, the surface of the marsh, just as the air's being let out of all the air and chyma in the root system. So you get subsidence following a mangrove mortality event. Also, now these mangroves, some of them were more than a metre in diameter. I'd say some of them were hundreds of years old, most of them decades old at least. In that period of time, you've had about 20 centimetres of silver-rise. So in the period between these mangroves establishing and now, you've got 20 centimetres of sea level rise and 10 centimetres of subsidence. I don't know the exact numbers, but it'd be thereabouts. So they're a third of a metre lower in the tidal frame compared to where they were when they established. And it seems that's enough. They're no longer mangrove, right? So the question is, and we've been asked this by local managers, do we replant them? Well, you can try. But maybe we're now saying this is seagrass, people. And the mangroves will probably happily march landward if they're given the opportunity. Sorry, it wasn't my final example. We're talking now, you've all heard probably about the mangrove dieback event in 2015. I have some very heretical ideas about what happened there. And here's me, 2015, 2016, I should say, here's me before and after photo. I like to think I've lost a bit of weight between 2015 and 2024, but it's probably just what I'm wearing. 2015, evidence of severe mangrove dieback. I wasn't aware at the time of taking this photo that was happening all across the north. 2024, there we have complete regrowth. And this is again this issue. They weren't dead. They were dying back. Putting this in a bit of a broader context, and I'm leaning here on the work of Leo Lindberner and Richard Lucas and others, who have looked at mangrove canopy effects right across Australia through time. And here they're looking at mangrove area, but also how much of that mangrove area is closed canopy versus open canopy. And this is one of the good news stories in Australia and indeed across the whole world. There's a paper that Dan Fries and his colleagues have just published in Science that shows that mangroves are really on the rebound globally, that the area of mangrove is increasing now. And certainly that's the case in Australia. And we sort of did a summary of this in 2022, where we showed that mangroves in Australia have been increasing consistently in area over at least the last 3 decades. And also that the amount of closed canopy in mangrove has been increasing over time. So that's a good news story. And that's partly driven by climate change, because mangroves are starting to move out into salt marshes and salt pans as sea levels rise, but they're not tending yet to erode at the seaward edge or die back at the seaward edge, other than local examples like Mile River. Also, they're increasing in canopy density, and that might be partly the CO2 fertilization effect. And so climate change, in a sense, is good for mangroves at the moment. Sea level rise is good for mangroves. It's good for blue carbon as long as it doesn't get too high. One intriguing thing, and this is where I've got some heretical opinions, is that if you take the Lindberner data set, and here I've detrended this overarching increase, and I've got here a 3-year running mean, so I'm smoothing the data away from some of the interannual drivers. What do the local patterns look like? And here I've got 2 different coastlines, 2 different sides of Australia in the top of Australia. And I'm looking at the top in what's the area of open forest and underneath what's the area of closed forest, and one becomes the other as they shift from one form to another over time. And I think you'll agree that, if you look at that, it does look cyclical. And if you measure the periodicity of that cycle, it's about 18 years. And if you compare it to tide range, it follows an 18-year pattern in the size of the tides, so that where you have lower than average tides, you have more open forest, and where you have higher than average tides, you have closed forest. And so the moon has an effect. And if you look at 2015, and this is the long phase tidal harmonics in the Gulf of Carpentaria in 2015, it was at a phase of minimum tide range. And if you look at the size of that effect in the Gulf of Carpentaria, it's about 1/3 of a metre. So the high tide's 1/3 of a metre lower in 2015. What effect's that having on the amount of closed canopy? Well, it's dying back, and it's even dying back from about 2010 onwards. And in 2015, the El Nino hits at the same time, so it means sea level is lower. A combination of those factors, lower mean sea level associated with the El Nino, and lower tide range by about 1/3 of a metre, and the mangroves are left high and dry. And for that reason, it's like a 1-2 punch. Thousands of kilometres of mangrove dieback in the Gulf of Carpentaria. I just thought it was a really interesting example. So looking at where are we going this year, and I just downloaded these data from Climate Reanalyzer. Where are we at with El Nino 3.4? This is that part of the Pacific Ocean that's a really good indicator of the strength of the El Nino. It's in completely uncharted territory at the moment. It's way above anything like 1998 or 2015, 2016. Where it goes from here, not exactly sure. NOAA have just declared a 60% chance of a very strong El Nino. I say that to say, okay, well, across the north of Australia, we are currently in semi-diurnal coastlines at the nodal cycle minima. We're moving into a strong El Nino. We might see some mangrove dieback across the north of Australia. Keep in mind that this is likely to be a short-term effect. The longer-term effect on mangroves at the moment of climate change is expansion. Mangroves are loving it. Okay, I'm going to turn part two and give you a bit of a guide, and this will just hopefully go for about 10 minutes or so, because we won't have time for questions. What are mangroves doing in terms of sea level rise, and what are they likely to do? I guess I've already made my first point, is that they're increasing in extent in Australia in relation to sea level rise, and also being restored around the world, sea level rise helping. I don't want to spend too much time on this other than to say that mangroves used to be in the Bonaparte Gulf and were absolutely swamped by sea level rise after the last glacial. And if you go down 70 metres into the ocean, you can still find mangrove peats down there. So in other words, there are thresholds at which mangroves will step back in relation to sea level rise. It just gets too high for them. And one of the advances in recent years is actually quantifying at what thresholds mangroves have to step back. They have to move landward. They can't keep up with sea level rise. And at what rates of sea level rise do they actually keep up? And we now know that that's probably around 7 millimetres a year of sea level rise. Anything lower than that is really not much of a threat to mangroves. They can accrete vertically at about that rate of sea level rise. And at the same time, they'll be moving landward, driven by sea level rise, so you get the expansion of mangroves. Higher than that, they tend to contract. And if you look at the paleo record, go back beyond 8,000, 9,000 years ago, you find very little evidence of mangroves. Not that they weren't there, but they weren't forming big forests. They were just kind of being driven back by silver-eyes across the landscape. And silver-eyes can get as high as 40 millimeters a year, which is 10 times what it is at the moment. Mangrove species survive if they're given the opportunity, but they won't form big forests. And as the rate of sea level rise decreased over the last 10,000 years, we're stepping away now from the deglaciation, sea level stabilizing. Mangrove vertical accretion pretty much tracks sea level rise. And so if sea level rise increases, you get an increase in the amount of mangrove vertical accretion. So they do have this inbuilt resilience to sea level rise. They can increase their elevation, the marsh surface elevation, the mangrove surface elevation, at about the same rate of sea level rise over very, very long periods of time, centuries to millennia. Once you get above 7 millimeters a year, it's like, there's no evidence in the paleo record that they can sort of keep up with that. We've also been looking in real time, and I'm sorry about the complexity of this illustration. It's highlighting a method we call the surface elevation table. And here we're trying to measure in real time the same thing. Are mangroves keeping pace with sea level rise? And essentially it's an elevation benchmark rod that goes deep into the ground. We're measuring change in the elevation of the marsh surface, hoping that the mangroves are actually keeping pace with the amount of sea level rise. And this is a network that extends right across the globe, well over 1,500 installations across the world, where we're in tidal marshes, mangroves. We were taking these painstaking measures. Are they keeping pace with sea level rise? And I guess to cut a very long story short, the answer is yes and no. Yes, as sea level rise increases, the rate of elevation gain increases, but they're soft sediment environments, and that sediment is always compacting. And so we have this process of subsidence going on at the same time. And in fact, the more accretion we have, the more subsidence we have, because that accretion weighs down the marsh below. And if you factor that in, you tend to find that once you get, and here's this magic number again, once you get to 7 millimeters a year of sea level rise, it's highly unlikely that the mangroves are going to be accreting at that rate. So we have a correspondence between what we have identified in the paleo record on the left-hand side and the observational record on the right-hand side. Almost a completely same profile of vulnerability to sea level rise. So we know we're onto something, two independent lines of evidence giving that confirmation that below 7 millimeters a year, they're probably going to be okay. Above 7 millimeters a year, probably not. And extrapolating to the end of the century across the globe, looking at different warming scenarios, here 2 degrees versus 3 degrees. Red is coastlines that exceed 7 millimeters a year by 2100. Very few coastlines get there under a 2-degree warming scenario. Almost all tropical coastlines reach that at 3 degrees. So the Paris Agreement target of keeping warming below 2 degrees is an absolute line in the mud for mangroves. Like if you're trending up toward 3 degrees, national commitments are at around 2.7. Nationally determined contributions takes us around 2.7 degrees. By 2100, that's danger zone for wetlands. So we want to make sure we keep things. Having said that, even though under 7 millimeters of sea level rise, you're essentially consigning wetlands to loss, it does take a long time. And just some modeling I've been doing with my colleague Jinfan Zhang It depends on geomorphic setting, but big river systems in the Indo-West Pacific, it can still take centuries. Even if you trip 7 millimeters a year of silver rise, it can still take centuries to lose your wetland, to lose your mangrove forest. If I'm on a coral island, it's probably just going to be in the next century. The Caribbean, Gulf of Mexico, places without a lot of sediment. Nah, we're talking decades. Big river systems with a lot of sediment, we're probably still talking centuries. So it's not a catastrophic situation for mangroves. But you're certainly on a slippery slope. Okay, so final slide, or penultimate slide. Resilient blue carbon, because we're interested in mangroves partly because they're carbon. I must make the point that climate change, silver rise, actually is enhancing mangrove blue carbon. It's increasing the amount of carbon because they respond to silver rise by building up their root mass. Make sure if you're wanting to plant mangroves, you've got what we call sufficient elevation capital, that you're high enough above that low tide threshold where they're likely to drown. In a 2-meter tide range, you've got 2 meters to play with, or a meter. You want to be above Australian height datum. That's pretty much rule of thumb. Lower threshold for mangroves is Australian height datum. You want to be above that. Higher the better in terms of your longevity. Is there a source of sediment that's going to subsidize the elevation gain in these mangroves that's going to give you a bit more capacity to survive? Mesotidal to macrotidal systems, more resilient, we think, than microtidal systems. Local subsidence. Is there any reason why the ground might be sinking anyway, accelerating the rate of silver rise? This is a big issue in Southeast Asia where there's a lot of groundwater extraction from coastal and where you have coastal floodplains that are subject to groundwater extraction, often you have very rapid rates of coastal retreat and mangrove loss. Wave climate, within estuaries, they're pretty well protected by high wave energy, and that's going to confer resilience. And to return to my opening point, lateral geomorphic stability, making sure that your site isn't exposed to lateral erosion. So I'm going to finish with a slide that gives 2 examples of what not to do. And embarrassingly, the first one is from Vera, showing someone happily planting in mangroves where they will never survive. I can promise you those mangroves did not survive 6 months, given that it's right at the bottom of the tidal frame and there are waves in the background. And sadly, also, the IPCC report, why you would plant mangroves in the middle of the ocean is beyond me. But that was the cover of the 2014 Working Group 2 report. I'm going to end it there. And I hope that wasn't too negative. I'm actually really positive about the prospects of mangroves and capacity for mangrove restoration. I think Dan Freese's paper is really exciting, that they're on the way back. And in Australia, in spite of local dieback here and there, they are on the increase, which is a good thing. Okay, I'm going to end the show. Stop sharing.
Thanks, Neil. Great.
No problem. Okay.
There's lots of applauding, clapping going on.
Fire away. Got some time for questions.
Yeah, you have. Thanks. That was brilliant. Thank you so much.